Okay, so in the previous video we looked at arrangements and the way to different ways to calculate the number of ways of arranging objects or people or whatever into certain positions given certain restrictions. And we found that generally speaking, if we have n objects to arrange into r positions, that's n PR, n permute into r positions, so p for permutations, and that's the same as n factorial over n minus r factorial. Okay. Today what we want to have a look at is selections. So this is for arrangements, not for selections. Okay, so selections differ from arrangements because the order in which we select the objects does not matter. Okay, so for example, if I have 8 people from which I'm trying to award first, second and third place getters, then that's an arrangement because the order that I choose the 3 people matters. Whereas if I am just trying to select a team of 3 people from 8 people, then that's a selection. And there are going to be fewer ways that I can select than there are to arrange, because for every selection of 3 people, there are then all those possible arrangements of those 3 people when it comes to considering arrangements, whereas they are all lumped together as just one selection. So we're going to have fewer selections than we do arrangements for given numbers of people and positions. Okay, so let's have a look at that example then. So in how many ways can I award first, second and third place from 5 people? So I'm just reducing the numbers to make it a bit simpler here to think about the options. So essentially this is asking me to select to arrange 5 people into 3 positions. So that would be 5p3, which is the same as 5 factorial over 2 factorial, 5 minus 3, that's how we get the denominator. And that's the same as simply 5 times 4 times 3. Okay, all those 3 things give me the same thing, and that's going to be 60. So there's 60 different ways that if I have 5 people that they could finish in first, second and third places, assuming they all have equal chance of finishing first. So then part B, in how many different ways can I select 3 people from 5 people? Alright, so you might want to think about, let's say we have 5 people, A, B, C, D and E. Okay. So obviously we could select A, B and C, or we could select A, B and D, or we could select A, B and E, or we could select A, C and D, A, C and B. No, that's the same selection as A, B, C, A, C and E. Okay, or we could select A, D and E. Okay. They're all the ones where we have to select A. So then if we forget the ones we have to select A, we could have B, C, D, we could have B, C, E. We could have B, D, E. And I think that's probably everything. Oh no, C, D, E, without A or B. C, E, D is the same selection, C, B, A is the same as A, B, C, etc. So essentially there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways to select. So let's think about how that's different from that. Okay, so that's 6, a factor of 6 less, that we've divided by 6. Okay, so that means there's 10 selections possible. So there's 60 arrangements, and there's 10 selections. Okay, which if we try and think about this, that is divided by 6. And the reason that that's divided by 6 is because for every one of these selections, there are three factorial ways we could arrange those. Okay, so for every one selection, there are 3 factorial different arrangements, which is 6. We've multiplied by 6. Okay, so therefore, if we can work out the number of arrangements, we then need to divide by the number of ways that we can arrange 3 things, in this case because we had 3 positions. So we actually need to also divide by 3 factorial. Okay. If we generalize that, so in this case we've divided by 6, which is actually dividing by 3 factorial to get that. So what we've actually done here is we've calculated the selections, which was 5 factorial over 2 factorial, but then we've also had to divide by the arrangements, which is 5 factorial divided by 2 factorial, but then we've also had to divide by 3 factorial. And this is actually a specific example of a really general rule for calculating selections. So if I think about this, what we've sort of done here is we could think about this in a slightly different way. So we could think about the fact that the number of different ways that 5 people could be arranged into first, second, and third place is to first choose the 3 people that finish first, second, and third, and then to think about the number of ways to arrange them. Okay, so essentially what we're saying here is that in the same way that the number of ways to arrange n objects in R positions is npr, the number of ways to select R objects from n objects is ncr. I read that, when we say that, we tend to read that as n choose R. The C actually stands for combinations. If we have n objects and we want to choose to select R combinations of those objects, how many ways can that be done? But NCR I always read as n choose R. I have 5 objects from which to choose 3. So therefore, in this particular case, the number of ways to select 3 people from 5 people, that's 5C3. Okay, this is number of different ways that we can arrange 5 people into first, second, and third. That's 5P3. Okay, and the number of ways to arrange 3 people is 3 factorial. So that's how we sort of get the formula which we've just come up with from there. So 5p3 is the same as 5 factorial over 2 factorial. That's equal to 5c3, which we've multiplied by 3 factorial. So 5c3 is the same as 5 factorial over 2 factorial, but also over 3 factorial. Okay, and we can generalize that. NCR is n factorial divided by r factorial times n minus r factorial. Okay, so essentially that is the selections, and then we're also dividing by r factorial to reduce the fact that it doesn't matter what order we choose those r things from in. Another commonly used alternative notation for NCR is to write it like this. It's not a matrix, it's not a fraction, it doesn't have a line in between. Okay, so 10, 2 would mean 10 choose 2. I tend to still write this, but just to be clear on that notation. In terms of your CAS menu, 5, we already know 1 is for factorial, 2 is for permutations, and 3 is for combinations, so that is NCR there. So we can just check. Up here, we worked out that this answer should have been 5 choose 3. If we do 5, 3, that should be 10, which is what we got here with our 10 selections. Okay, so that first example is really just to establish our rule for NCR, and now we know that we can use NCR. We use NCR of all the things in this little topic of counting methods. NCR comes up next year. Permutations, arrangements tend to really just be a year 11 topic, but we need NCR in the context of something else next year, in the context of the binomial distribution, which is why we've pushed quite hard to still cover this content this year. Okay, the other thing is that some simple values of NCR can be easily evaluated if we understand the patterns that happen. So I'm just going to use my calculator to evaluate each of the following. Some of them you might be able to think through. 0 choose 0 is a slightly technical one, and that's because if I've got no objects and I want to choose none of them, there's actually one way to do that, which is to choose nothing. Okay, and you can confirm that with NCR 0 choose 0 is 1. Okay, that's a slightly technical definition. But the rest are fairly straightforward. If I have one object and I don't want to choose any of them, there's one way to do that. If I have one object and I want to choose one of them, there's only one way to do that. Okay, and again, you can confirm that. Menu 5, 3, 1 choose 0 is 1. Menu 5, Menu 5, 3, 1 choose 1 is also 1. Okay. If you think about that same pattern, it wouldn't matter how many objects you have to choose from. If you want to choose none of them, there's one way you can do that, which is to choose none of them. So these are all going to be 1s down here. 3 choose 0, 4 choose 0, 5 choose 0, menu 5, menu 3, 5, 3. In fact, I'm wondering if I type x choose 0 in here, it will tell me that that's 1. Right, so it doesn't matter what x is, it'll be 1. Similarly, if I wanted to had two objects and I want to choose 2 of them, or 3 objects and I want to choose 3 of them, or 4 objects and I want to choose 4 of them, there's only one way to do that. And again, I think we can probably generalize that with our CAS. If we say we have x objects and we want to choose x of them, that will always be 1. Okay, then the others, we might start to need our CAS a little bit more. So if we have 2 objects and we want to choose only one object, there's going to be 2 ways to do that. We could choose the first object or the second object. Okay. If we have 3 objects and we want to choose only one object, there's 3 ways to do that. We could choose the first object or the second object or the third object. Okay. Similarly, if there's 4 objects from which we choose one, 4. If there's 5 objects from which we choose one, 5. Okay. Again, I think we could probably menu 5.3. If we have X objects from which we want to choose one object, there should be X ways to do that. Correct. Okay. Now, interestingly, this diagonal is going to be the same as this diagonal. And that's because if you have 3 objects, so let's say we have objects A, B, and C, and we want to choose 2 of those objects, we could either choose A and B, or we could choose B and C, or we could choose A and C. There's 3 ways to do that. Okay. The key is it's the same question as asking how many ways are there to choose one object from 3 objects, because essentially by choosing to keep 2 objects, we are automatically choosing to reject one object. So if we're choosing 2 objects from 3 objects, by default that's the same number of ways we can choose only one object. We could choose object C, we could choose object A, we could choose object B. Okay. So it's the same question, because when you're choosing 2 objects, it's the same as choosing to leave one object behind. So essentially we get this nice symmetry happening here. So there'll also be 3 ways if we want to choose 2 things out of 3 things. There will also be 4 ways to choose 3 things from 4 things, because we're essentially choosing 1 thing from 4 things to leave behind. Okay. And similarly this will be 5. We can confirm that. Menu 5.3, if I had 20 objects and I want to choose 19 of them, there should be 20 ways to do that. And that's the same as if I had 20 objects and I want to choose one of them. Okay. Right, so I'm generalizing some of these patterns here. We've actually talked through these 4 patterns down the bottom here. So if I have anything and I want to choose nothing, there's one way to do that. If I have any number of things and I want to choose all of them, there's one way to do that. If I have any number of things and I want to only choose one of them, there's n ways to do that. If I have n things, and if I have n things and I want to choose n minus 1 of them, that's also going to be n things, because it's the same as that. Same as choosing one thing. Okay, I'll use my CAS for these last couple. Menu 5.3, 4 choose 2 is 6. Menu 5.3, 5 choose 2 is 10. Menu 5.3, 5 choose 3 should also be 10. Oh, sorry. 5 choose 3 should also be 10, because again, these are the same question. If I have 5 objects and I want to select 2 of them, I am at the same time selecting 3 of them to be left behind. So it's the same as choosing 3 things. Okay, so we can actually generalize that even further. That if I have NCR, that's the same as NC, N minus R. So for example, 60 choose 13 would be the same as 60 choose 47, which is 60 minus 13. We can confirm that. I've probably chosen big numbers, they're going to give me big answers, but let's see. Okay, so there's that many ways, and if I did 60 choose 47, it's the same. Okay. Alright, so this is something called Pascal's triangle, alright, and if you look at the numbers, you build up this triangle with 1s down the sides, okay, and then each number after that, each other number is obtained by adding together, sorry that highlight is hard to see, adding together the 2 numbers diagonally above. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5. So we could also write the next row would be 1, 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, 5 plus 1 is 6, and a 1. Okay, and each of these values would correspond to the values for 6 choose something. So this would be 6 choose 0, this would be 6 choose 1, this would be 6 choose 2, this would be 6 choose 3, 6 choose 4, 6 choose 5, and 6 choose 6. 6. Okay, and so we can actually generate the triangle quite quickly and easily, and hence find some simple combinations without use of your CAS, and that's important next year when we often need those in a tech-free exam, for example. Okay, let's work through some examples with selections. So a pizza restaurant offers the following toppings: onions, green peppers, mushrooms, anchovies, and pepperoni. Okay, so we have 1, 2, 3, 4, 5 topping options. Okay. How many different types of pizza with 3 toppings can be ordered? Okay, so the key is that the order that you apply the toppings doesn't matter. If you order a pizza with mushrooms, anchovies, and pepperoni, the person asking for your order doesn't ask you which order you want them to put those things on the pizza. Okay, so it's not an arrangement, it's just a selection. We have 5 different pizza toppings from which we want to choose 3. I apologise that those numbers are the same as ones we've looked at before. Should have chosen extra pizza toppings. So there is 10 different pizzas with 3 toppings that we can select. Okay, so 10 pizzas. How many different pizzas with any number of toppings between none and all 5 can be ordered? Okay, now I agree that a pizza with no toppings is probably not a pizza, but let's say every pizza has the tomato sauce and the cheese. So therefore a pizza with none of these toppings is just a margherita pizza. Okay, so we can have any number of toppings between none and all 5. Okay, so if we have no toppings, there's going to be 1 pizza. That is 5 choose 0, which is 1. Okay. If we have 1 topping, it's going to be 5 choose 1, which will be 5. If we have 2 toppings, it's going to be 5 choose 2, which will be 10. Okay, and so we're going to need to go all the way up to the 5 toppings. Okay, so that means what we're essentially saying here is that we could have no toppings, or so plus we could have 1 topping, or so plus we could have 2 toppings, or so plus we could have 3 toppings, or so plus we could have 4 toppings, or we could have 5 toppings. So essentially that's just adding together the entire row, the 5th row of the Pascal's triangle. Bearing in mind that we call it the first row is sort of the 0th row. First row, second row, third, fourth. If you call the first row the 0th row, the 0 row, it's easier then to see that the 5th row will be 5 choose 0, 5 choose 1, 5 choose 2, etc. Okay, so we're simply adding together that row, which is going to be 10 plus 10 is 20, plus another 10 with the 2 5s is 30, plus the 2. So that's going to equal 32. Now, interestingly, if we have a look at this pattern, sorry, I know my Pascal's triangle is getting a bit messy here. If we have a look at adding up the 4th row, 6 plus 4 is 10, plus another 4 is 14, plus 2 is 16. So this is 16. This is 3 plus 3 plus 1 plus 1, that's 8. This is 2 plus 1 plus 1 is 4. This is 2, and this is 1. Now these are all powers of 2. This is 2 to the 0, this is 2 to the 1, this is 2 to the 2, this is 2 to the 3, 2 to the power of 4, sorry, and 2 to the power of 5. So if we're adding up a complete row, it is just 2 to the power of whatever the n value of that row is. Okay, so this is 32. It's actually the same as 2 to the power of 5, and it is 32. And that's sort of because we actually could also think about this as a sort of pigeonholing arrangement problem. So there's lots of different ways to think about these kind of problems. So you could think about, okay, I have 5 toppings. Each topping is, I've got onion, peppers, mushrooms, anchovies, and pepperoni. Okay, so let's call this green peppers and pepperoni. Now, I can choose whether to have onions or no onions. So that means there are 2 options when it comes to the onions. And I can choose whether to have green peppers or not. So there are 2 options when it comes to the green peppers. 2 options with the mushrooms, 2 options with the anchovies, and 2 options with the pepperoni, which is where I get my 2 to the power of 5, which is 32. Okay, so lots of different ways to kind of think through these problems. All right, example 3. The selectors of a sporting team need to choose 10 athletes from the 15 track and 12 field athletes who have qualified to compete. How many different groups of 10 athletes could be selected? Okay, so in part A, there's no restrictions whatsoever. We've got 25 athletes to choose from. We've got 27 athletes to choose from, 15 track and 12 field athletes, and we just want to choose 10. Okay, with no specification of how many of each type we want. So that is simply going to be 27, choose 10. So menu 5.3, 27, choose 10. Okay, there is 8,436,285 different options if there are absolutely no restrictions about how I can choose those 10 athletes from the 27. How many different groups of 10 would contain track athletes only? Okay, so this time, now we're not selecting from the full 27, we're now just selecting from the 15 track athletes. So if we only took a full team of 10 track athletes, we have 15 track athletes to choose from, it'd be 15 choose 10, and so that's only 3,003 different teams we could select. How many different groups of 10 would contain half track athletes and half field athletes? Okay, so now we have 15 track athletes from which we want to choose only 5, and so multiply, we have a further 12 field athletes from which we want to choose 5. So it would be menu 53, 15 choose 5, multiplied by menu 53, 12 choose 5. So from the 12 field athletes we want to choose 5, and so multiply it from the 15 track athletes we want to choose 5. Okay, so there would be 2,378,376 different teams with half track and half field. Okay, so the work today is from exercise 10C, just questions 5 to 20.